Every comet we've ever tracked has followed one simple rule. It arrives, it leaves, it never comes back. But 3i Atlas might be about to break that rule in the most spectacular way possible. New simulations suggest this interstellar visitor isn't planning a flyby in March 2026. It's planning a parking maneuver. We're talking about an object from another star system potentially becoming Jupiter's newest moon. Except this moon could destabilize an entire planetary system, trigger an international crisis, and force humanity to rewrite the laws that govern space itself. Stay with me until the end, because what happens next involves crashed moons, nuclear rockets, and a salvage race that could redefine our place in the cosmos. The countdown has already begun. If you're as captivated by this mystery as I am, go ahead and like this video and subscribe so you stay connected as this story develops over the coming months. Leave a comment telling me where you're watching from, what hour it is in your corner of the world, and whether you think we're being told everything about what's going to happen out there near Jupiter. Part 1. The March. 2026. Surprise the new capture simulations. What if our interstellar visitor doesn't leave but stays? That's the question keeping astronomers awake at night as we approach March 2026. Because something extraordinary is about to happen at Jupiter, and depending on which simulations you believe, it could change everything we thought we knew about how the solar system works. The object in question is 3i Atlas, the third confirmed interstellar visitor to enter our solar system. It came from somewhere beyond the Sun's gravitational reach, moving on a trajectory that should carry it right back out into the cosmic void. Should being the operative word here. 3i Atlas was discovered hurtling through space at speeds that marked it as definitively not from around here. The numbers don't lie. This thing is moving on what astronomers call a hyperbolic orbit, the kind of path that screams just passing through. It's the cosmic equivalent of a road trip with no intention of stopping. The object showed all the hallmarks of a typical interstellar comet. A bright coma of gas and dust, visible tails streaming behind it, the whole works. NASA catalogued it. Scientists observed it. Everyone agreed it would make a close approach to Jupiter and then fling itself back into interstellar space, never to be seen again. End of story. Except some research groups are now suggesting the story might not end that way at all. New simulations have emerged over the past few months, and they're proposing something that sounds frankly insane at first hearing. These models suggest that 3i Atlas might not just swing past Jupiter in March 2026. Instead, it could execute what's called an aerocapture maneuver, using Jupiter's upper atmosphere or its own propulsion to shed enough velocity that it becomes gravitationally bound to the giant planet. In other words, it could park itself in orbit around Jupiter. Permanently. Now, let me explain why Jupiter matters so much in this scenario. Jupiter is the gravitational heavyweight champion of the solar system. It has more mass than all the other planets combined. When you're trying to capture an object moving at interstellar speeds, you need something with serious gravitational muscle to slow it down. Earth couldn't do it. Mars couldn't do it. Saturn probably couldn't do it. But Jupiter has the gravitational influence to make capture theoretically possible. Recent studies on interstellar object dynamics have shown that giant planets, particularly Jupiter, are the most effective places in any solar system for capturing incoming visitors. The physics checks out. The timing is remarkably specific. Multiple orbital propagation models are clustering around March 16th, 2026, as the date of closest approach. That's when 3i Atlas will either sail past Jupiter on its way back to the stars, or it will do something unprecedented. The uncertainty ranges are wide, sure, but the fact that researchers are even discussing this as a possibility should tell you something. This isn't fringe science anymore. There's even a published intercept plan for the Juno spacecraft targeting that exact date, which suggests that some people in the space community are taking this scenario very seriously indeed. So how would this capture actually work? There are two main mechanisms being discussed, and we'll explore them in detail later, but here's the overview. The first is natural gravitational braking through what's called three-body interactions. Imagine Jupiter, 3i Atlas, and one of Jupiter's many moons playing a complex gravitational dance that results in the interstellar object losing just enough velocity to become trapped. It's like cosmic billiards, except the balls are miles across and moving at tens of thousands of miles per hour. The second mechanism is more controversial and requires assuming that 3i Atlas isn't entirely natural. If the object has some form of propulsion system, either active engines or ablative materials that produce thrust when heated, it could execute a powered deceleration. Alternatively, it might perform an aerocapture maneuver, dipping into Jupiter's outer atmosphere to use atmospheric drag as a brake. This is a technique that spacecraft engineers have designed for missions but never actually implemented. The idea that a natural comet would do this accidentally strains credibility. But the idea that something might do it intentionally, that opens a whole different set of questions. Here's why this is so controversial and surprising. Conventional wisdom in astronomy treats hyperbolic interstellar objects as tourists. They come, we observe them, they leave. That's been the pattern with 1I/Oumuamua, the first confirmed interstellar visitor. That's been the pattern with 2I/Borisov, the second. Both of those objects flew through the inner solar system and kept right on going. The idea that 3i Atlas might break that pattern and become a permanent resident fundamentally challenges how we think about these visitors. And if it does capture, everything changes. Not just for astronomy, but for planetary science, for international relations, for how humanity sees itself in the cosmos. Because a captured interstellar object orbiting Jupiter wouldn't just be a scientific curiosity. It would be the most accessible sample of matter from another star system that we've ever had. It would be close enough to reach with spacecraft, close enough to study in detail, close enough to potentially touch. The stakes couldn't be higher. We're not talking about a distant observation anymore. We're talking about an object that could become a permanent feature of our solar system neighborhood, orbiting the largest planet just a few years' journey from Earth with current propulsion technology. An object that might hold answers to questions we've been asking for centuries about what else is out there. But before we dive into wild speculation about alien probes and salvage missions and geopolitical scrambles, we need to ground ourselves in what we actually know. We need to look at the data, examine the observations, and understand exactly what 3i Atlas has been doing since we first spotted it. Because the details, as they say, are where the devil lives. And there are some very interesting details emerging from telescopes around the world. So what do we actually know about 3i Atlas so far? Part 2. The breaking flash. What we expect to see the moment it captures. Imagine you're watching Jupiter through a telescope on the night of March 16th, 2026. You've been tracking 3i Atlas for weeks as it approaches the giant planet. Then, suddenly, you see a flash. Not a subtle brightening, but a genuine, unmistakable burst of light near Jupiter's cloud tops. Bright enough to see from Earth. Bright enough to make you question what you just witnessed. That flash, if it happens, would be the signature of aerocapture in action. Aerocapture is one of those concepts that sounds simple, but involves physics so violent it's hard to imagine. The basic idea is this. A spacecraft, or in our case a comet-like object, approaches a planet at high speed and deliberately dips into the upper atmosphere. The atmospheric drag acts like a brake, slowing the object down. If the maneuver is executed correctly, the object loses just enough velocity to become gravitationally bound without burning up or bouncing back into space. It's a knife-edge calculation. Too shallow an entry and you don't lose enough speed. Too steep and you become a fireball. Spacecraft engineers have studied aerocapture for decades because it's incredibly efficient. Chemical rockets require enormous amounts of fuel to slow down and enter orbit around a distant planet. But aerocapture uses the planet's own atmosphere to do the work. The problem is that nobody has ever actually done it with a real mission. It remains theoretical, at least for human spacecraft. The risks are too high, and the engineering challenges too severe. But 3i Atlas isn't a carefully designed spacecraft. If aerocapture happens here, it would be something else entirely. The predicted observational signature of such an event would be dramatic. We're talking about an object moving at tens of kilometers per second hitting atmospheric molecules. The compression and heating of the air in front of the object would create a massive shock wave. Temperatures would spike into the tens of thousands of degrees. The result would be a bright thermal flash, possibly accompanied by spectral signatures of atmospheric gases being ionized and excited. Some researchers have suggested this flash could be more energetic than the famous Shoemaker-Levy 9 impacts in 1994, when fragments of a comet slammed into Jupiter and created visible scars in the planet's atmosphere that persisted for months. Would we actually be able to see this from Earth? That depends on several factors: the timing of the event, which side of Jupiter is facing us, the brightness of the flash, and how quickly it fades. Jupiter is far away, between 4 and 6 astronomical units, depending on where Earth and Jupiter are in their respective orbits. That's between 370 million and 550 million miles. Even a massive explosion can look pretty small from that distance. But modern telescopes are sensitive. Space-based observatories like the James Webb Space Telescope or Hubble could potentially capture the event. Ground-based facilities with adaptive optics might see it too. And here's something interesting. We already have observers in position. The JUICE mission, the Jupiter Icy Moons Explorer launched by the European Space Agency, has recently captured images of 3I Atlas showing its coma and tails. JUICE is en route to Jupiter right now and will arrive in the early 2030s, but its instruments are active and capable of long-range observations. If something dramatic happens during the March 2026 approach, JUICE could have a front-row seat. Other Jupiter monitoring assets, both space-based and ground-based, will be watching too. Now here's the part that makes some scientists extremely uncomfortable. A bright flash from aerocapture is not something you'd expect from a normal comet. Regular comets do produce coma and tails through outgassing. As ice sublimates from the comet's surface, it releases gas and dust that reflects sunlight, creating the characteristic fuzzy appearance and streaming tails we associate with comets. But this process is relatively gentle. It doesn't produce sudden violent bursts of energy at the scale we're talking about with aerocapture. To get that kind of energy release from a natural comet, you'd need something catastrophic, a major collision, a sudden structural failure, maybe a massive explosive outburst from volatile pockets inside the nucleus. These things can happen, but they're rare and usually unpredictable. A controlled aerocapture maneuver, by contrast, would be deliberate, timed, executed at a specific altitude and velocity to achieve a specific outcome. That's what makes the idea so provocative. If we see a flash, and if that flash coincides with 3I Atlas entering a bound orbit around Jupiter, it becomes very difficult to explain through natural processes alone. Of course, the counter-argument is immediate and strong. The overwhelming majority of scientists who have studied 3I Atlas say it looks and behaves like a comet. Period. Official statements from space agencies and observatory directors emphasize that current observations remain entirely consistent with a natural object. No radio signals have been detected, no artificial structures have been resolved. No technosignatures of any kind have appeared in the data. The spectral analysis shows water, carbon dioxide, carbon monoxide, dust, exactly what you'd expect from a comet nucleus. From this perspective, the capture scenario is interesting, but the idea that it's engineered is pure speculation without evidence. Fair enough. Science demands skepticism, and extraordinary claims require extraordinary evidence. We don't have that evidence. Not yet. But here's why this matters anyway. Aerocapture is one of the few scenarios that would produce an observable, dramatic, unambiguous signature that something unusual is happening. Most of the time in astronomy, interesting events are subtle. They show up as slight variations in light curves or minor spectral anomalies or statistical patterns that take months to confirm. An aerocapture flash would be different. It would be obvious, immediate. The kind of thing that makes people drop what they're doing and stare at their monitors. If we're going to watch for anything on March 16th, 2026, this is it. So what should astronomers be looking for? Here's the watch list. First, thermal signatures in the infrared. A hot shock wave would radiate strongly in wavelengths that infrared telescopes can detect. Second, spectral lines indicating ionized atmospheric gases, hydrogen, helium, maybe even more complex molecules if Jupiter's upper atmosphere is churned up. Third, visible light brightening at specific locations relative to Jupiter's position. Fourth, timing. Does the flash correspond exactly to the predicted closest approach? Fifth, aftermath. Does 3I Atlas's trajectory change? If it's on a hyperbolic orbit before the flash and an elliptical orbit afterward, that's your proof. Any one of these observations alone might have alternative explanations. All of them together? That would be hard to dismiss. But you know what? Before we get ahead of ourselves imagining bright flashes and capture events, we need to address something that's been bothering a subset of the astronomical community for months now. Some observers argue that even the orbit doesn't fit a natural comet. They claim there are oddities in the trajectory, subtle but persistent, that suggest something more than simple Newtonian mechanics and random outgassing. Microcorrections, they call them. Course adjustments. Deviations that can't be easily explained. Are they right? Or are they seeing patterns in noise? Let's dig into the trajectory data and find out. Part 3. Why the trajectory looks wrong for a natural object. When astronomers track a comet, they expect certain behaviours. The object follows a predictable path determined by gravity, modified slightly by something called non-gravitational forces. These forces come from outgassing. As ice turns to vapour on the sun-facing side of the comet, it creates jets that push the nucleus in various directions. It's like a very inefficient rocket engine firing randomly. Over time, these jets cause small but measurable changes in the comet's orbit. Scientists have models for this. They know how to account for it. The math works. For 3I Atlas, the official classification is straightforward. It's an interstellar comet on a hyperbolic trajectory. NASA's catalogues list it as such. The observations show coma, tails, dust production, all the hallmarks of a comet actively outgassing as it approaches the sun. The spectral data confirms the presence of volatiles, water ice, carbon dioxide ice, carbon monoxide, maybe some ammonia and methane. Everything checks out. From the perspective of mainstream astronomy, 3I Atlas is unusual because it's interstellar, but it's not unusual in its behaviour. It's doing what comets do. But then you start hearing whispers from the fringes. Independent analysts, amateur astronomers, a few researchers who aren't speaking for the record. They're looking at the same trajectory data and seeing something that bothers them. The official orbit shows a smooth hyperbolic path with small perturbations from outgassing, yes. But these observers claim the perturbations aren't quite random enough. They detect what they describe as microcorrections, subtle trajectory adjustments that seem too precise, too well timed, to be explained purely by chaotic comet activity. Now, let me be very clear. These claims are speculative and contested. No peer-reviewed paper has definitively proven that 3I Atlas is behaving anomalously. The people making these claims are, in some cases, working with publicly available data and their own analysis tools, not official observatory resources. Some of them have agendas. Some of them are prone to seeing patterns that aren't there. You have to approach these claims with healthy skepticism. But you also have to ask, what if they're not entirely wrong? Non-gravitational acceleration is the technical term for what happens when a comet's motion deviates from pure gravitational predictions. For a typical comet, this acceleration is driven by outgassing jets. The gas molecules escaping from the surface carry momentum, and by Newton's third law, they push the nucleus in the opposite direction. The magnitude and direction of this force depends on where the jets are located on the surface, how active they are, and how the comet is rotating. It's messy and complicated, but it follows physical principles we understand. With 3I Atlas, some analysts claim the non-gravitational acceleration doesn't quite fit the standard outgassing model. They point to small velocity changes that occur at times when the comet's activity, as measured by brightness and coma size, doesn't suggest strong jetting. Or they note directional biases in the acceleration that seem inconsistent with random jet orientations. One claim, unverified but persistent, is that the trajectory shows signs of anticipatory correction, as if the object is adjusting its path to compensate for perturbations before they fully manifest. This is where things get weird. Anticipatory correction would require either an incredibly fortunate alignment of natural processes or something that can sense and respond to external forces. A comet can't do that. A comet is a lump of ice and rock tumbling through space. It doesn't have sensors or control systems, so if the trajectory really does show this kind of behaviour, either we're misinterpreting the data, or 3I Atlas isn't entirely a comet. Alternative hypotheses exist that don't invoke alien technology. Maybe 3I Atlas has outgassing jets that are unusually symmetric or unusually stable, producing thrust patterns that mimic controlled flight. Maybe the nucleus has an odd shape or rotation that causes the jets to fire in specific directions at specific times, creating a pattern that looks deliberate but is actually just geometry and timing. Maybe we're simply looking at measurement errors amplified by observer bias. People who want to see anomalies will find them, even in perfectly normal data. But here's where recent scientific literature adds an interesting wrinkle. A 2025 study on interstellar object capture used N-body simulations to show that under certain conditions, ISOs can indeed be captured into bound orbits via gravitational braking by giant planets. The study found that captured objects tend to end up on high eccentricity, inclined orbits that look nothing like the circular equatorial orbits of regular moons. If 3I Atlas were to be captured, its orbit would be exotic, strange, unlike anything native to the Jupiter system. And here's the kicker. The study suggests that the capture process itself might involve complex multi-body interactions that could, in principle, produce trajectory variations that mimic non-random behavior. In other words, even if 3I Atlas is completely natural, the process of approaching Jupiter and potentially being captured could create orbital quirks that look suspicious to analysts who aren't familiar with the full dynamical context. That's a plausible explanation for the claimed anomalies. It doesn't require anything artificial. On the other hand, it doesn't rule it out either. The recent statements from mission scientists emphasize that no technosignature has been observed. That's important. A technosignature is any evidence of technology. Radio transmissions, laser pulses, organized structures, materials or geometries that can't form naturally. If 3I Atlas were an alien probe, you'd expect it to give off some kind of signal or show some kind of artificial feature. So far, nothing. The spectral data shows natural materials. The light curve shows behavior consistent with an irregular rotating nucleus. The morphology of the coma and tails fits comet models. By every conventional measure, this is a comet. But technosignatures assume we know what to look for. If an advanced civilization built a probe to travel between stars, would it necessarily broadcast radio signals? Would it have shiny metal surfaces that reflect light in obvious ways? Maybe. Or maybe it would be designed to look exactly like a natural object to avoid detection. Maybe the entire outer layer is comet material, deliberately accumulated or grown, hiding whatever lies underneath. That's speculation piled on speculation, but the point is that absence of obvious evidence isn't the same as evidence of absence. The data is insufficient to declare the orbit anomalies definitive. Measurement errors, natural jet activity, or the complex dynamics of approaching Jupiter could all explain the variations. But the data is also insufficient to rule out something more unusual. That uncertainty is what makes the March 2026 window so critical. If 3I Atlas executes a capture maneuver that looks controlled, if the trajectory changes in ways that can't be explained by gravitational interactions alone, that's when the claims of anomalous behavior will either be validated or demolished. And here's something that should make you sit up and pay attention. If the orbit is already showing small, hard-to-explain deviations, the margin between a flyby and a capture could be smaller than conventional models suggest. A tiny velocity change, a slight adjustment in approach angle, and what should have been a hyperbolic escape becomes an elliptical trap. The difference might come down to a few hundred meters per second. That's nothing on an interstellar scale, but it's everything for whether 3I Atlas stays or goes. So we're left with questions. Is the trajectory genuinely anomalous, or are we seeing what we want to see? Is 3I Atlas responding to external forces in ways that natural comets can't, or are we underestimating how weird natural comets can be? And if it does capture in March 2026, will we be able to tell whether it was an accident of orbital mechanics or something more deliberate? The answers are coming. But assuming the worst-case scenario, or maybe the wildest-case scenario, there's another problem that's been quietly bothering people who've looked at 3I Atlas's behavior closely. The mass doesn't add up. This thing acts heavier than it has any right to be, and if it really is more massive or more dense than a typical comet, that changes everything about what happens if it captures. Let's talk about the mass problem. Part 4. The mass problem. Why Atlas acts. Denser than it has any right to be. Comets are not dense objects. They're often described as dirty snowballs, but that's almost giving them too much credit for solidity. A more accurate description would be fluffy ice rubble loosely held together by its own weak gravity. Typical comet densities range from about 0.3 to 1.0 grams per cubic centimetre. For context, water ice is about 0.9 grams per cubic centimetre, and solid rock is around 3. So comets are basically barely held together piles of ice and dust with lots of empty space between the particles. They're fragile. When comets get too close to the sun or experience too much tidal stress, they sometimes just fall apart. 3I Atlas, based on observations, has a nucleus somewhere between 440 meters and 5.6 kilometers across. That's the estimated range based on brightness measurements and assumptions about how reflective the surface is. Hubble Space Telescope observations helped pin down the upper limit. Smaller telescopes provide the lower bound. The exact size matters because it tells us how much volume we're dealing with, and volume plus density gives you mass. If you assume 3I Atlas is a normal comet with normal comet density, you can calculate its mass. The result is something on the order of billions of tons if it's on the larger end of the size estimate, or perhaps millions of tons if it's smaller. That sounds like a lot, but in space terms it's actually tiny. For comparison, Jupiter's moon Io, which is about the size of Earth's moon, has a mass of about 90 trillion kilograms. Even the small inner moons of Jupiter that we'll talk about later have masses measured in the tens of trillions of kilograms. 3I Atlas, by conventional estimates, would be a pebble compared to Jupiter's existing satellites. But here's the thing. Some of the observed behavior, particularly the orbital dynamics and the claimed non-gravitational accelerations, seem to suggest something heavier. The way 3I Atlas responds to gravitational tugs, the way it affects and is affected by nearby bodies, doesn't quite match what you'd expect from a fluffy comet nucleus. Now, this is where we have to be careful. Because we don't have direct mass measurements, we can't just put it on a scale. Mass estimates come from indirect observations, and they have large uncertainties. But the mismatch has caught some people's attention. Here's the speculative idea, and I want to emphasize that this is speculation. What if 3I Atlas isn't a homogeneous ball of ice and dust? What if it has a core? Specifically, what if there's an ultra-dense core, maybe metallic, maybe made of exotic materials we don't have names for, surrounded by a relatively thin shell of typical comet material? The outer layer would sublimate and create the coma and tails we observe, making it look like a normal comet from the outside, but the inner core would provide much more mass than the size suggests, making the object substantially denser overall. Why would nature create such a thing? It probably wouldn't. Metal-rich asteroids exist, sure, but they don't have thick ice mantles. Comets exist, but they're ice and rock, not metal cores wrapped in frost. You could imagine some exotic formation scenario, maybe involving the core of a differentiated planetesimal from another star system, that got ejected and then accumulated ice during its journey through interstellar space. That's theoretically possible, but seems like a lot of coincidences stacked on top of each other. Or you could imagine something built, designed, a dense structural core for payload or propulsion or whatever purpose, covered in comet material either for disguise or for protection during interstellar travel. That starts to sound like science fiction, but given everything else we're discussing, it's worth considering as a hypothesis. What would a dense core imply for Jupiter capture? It would imply a lot. Gravitational capture depends on the object's mass because more massive objects are harder to slow down. But if 3I Atlas does manage to capture despite being denser than expected, that would mean it brought more momentum into the Jupiter system than a typical comet would. And once it's in orbit, a more massive object exerts stronger gravitational influence on everything around it. That includes Jupiter's moons and rings. Let's do a thought experiment. Imagine an object with, say, 10 times the density of a normal comet enters a retrograde orbit somewhere in Jupiter's inner satellite system. Retrograde means it's orbiting opposite to the direction of Jupiter's rotation and opposite to the orbits of most moons. This is important because retrograde orbits are inherently unstable when you have lots of other objects moving prograde. Gravitational interactions are stronger and more chaotic. Now add in that this object is much heavier than it appears. Every time it passes near a moon or through a ring region, its gravity tugs on those structures. Over time, those tugs accumulate. Orbits that were stable for billions of years start to shift. Resonances that kept moons in perfect coordination begin to break down. Small perturbations grow into large instabilities. This is basically the nightmare scenario for Jupiter's ring system, which we'll explore in detail in the next part. But the key point here is that the mass of 3I Atlas directly determines how much chaos it can cause. A fluffy comet with normal density, even in a retrograde orbit, probably wouldn't do much damage. It's just not gravitationally significant. But a dense imposter with a heavy core, that could wreak havoc. Now, mainstream astronomers would push back hard on this scenario. They'd point to the fact that the observed brightness and the observed dust and gas production rates all match what you'd expect from a comet with normal composition. Recent studies of 3I Atlas's pre-perihelion activity found dust production consistent with other comets. The light curve behaves like a rotating irregular nucleus would behave. Nothing in the optical or infrared data screams metal core. The spectral signatures are volatiles, water, carbon dioxide, carbon monoxide, exactly what comets are made of. But here's where things get interesting. A very recent preprint, published in 2025, analysed 3I Atlas's composition in detail using spectroscopic observations. What they found was striking. The ratios of carbon dioxide to water and carbon monoxide to water are extremely high, much higher than typical solar system comets. In fact, the carbon dioxide to water ratio is among the highest ever measured for any comet. The study suggests this composition is the result of processing by galactic cosmic rays over millions of years of interstellar travel. Cosmic rays are high-energy particles that permeate the galaxy. When they strike the surface of an object, they can break chemical bonds and rearrange atoms. Over long timescales, this process can convert simple ices into more complex molecules and can alter the surface chemistry dramatically. For 3I Atlas, which has likely been travelling through interstellar space for tens of millions of years, cosmic ray processing could have created a hardened, chemically altered crust enriched in carbon dioxide and organic compounds. The study found that only the outer 15 to 20 meters of the nucleus are being sampled by outgassing, meaning we have no direct information about the interior composition. So the exterior chemistry is weird because of cosmic ray processing, and we know nothing about what's underneath. That leaves the door open for the dense core hypothesis, even if it's unlikely. The processed crust could be hiding anything, or the crust itself could be denser than normal due to compaction and chemical changes from radiation exposure. Either way, the idea that 3I Atlas might be substantially denser than it appears isn't completely ruled out by observations. If 3I Atlas is denser than any known comet, natural or otherwise, could this be the single most important factor enabling a stable capture around Jupiter? Mass is destiny in orbital mechanics. A heavier object requires more energy to capture, yes, but once captured, it's more stable against perturbations. It's also more dangerous to existing structures because it can't be easily nudged or ejected. If 3I Atlas settles into orbit with significant mass, it becomes a permanent fixture that Jupiter's system will have to accommodate. The moons, the rings, everything will adjust to its presence, whether they want to or not. And that brings us to the most visually spectacular and scientifically terrifying possibility of all. What happens to Jupiter's rings if this object stays? Part 5. If it stays, Jupiter's ring system enters the danger zone. Most people don't even know Jupiter has rings. That's because they're faint, thin, and made mostly of dust rather than the impressive ice chunks that make Saturn's rings so photogenic. You need a good telescope and the right angle to see Jupiter's rings at all, and even then they're not much to look at. But just because they're subtle doesn't mean they're simple. Jupiter's ring system is a delicate, finely tuned structure maintained by a handful of tiny inner moons that act as gravitational shepherds. These moons keep the ring particles confined, prevent them from spreading out or falling into the planet. It's a balance that's been stable for perhaps billions of years. The inner moons we're talking about have names like Metis, Adrastea, Amalthea, and Thebe. They're small, ranging from about 10 kilometers across for the smallest, up to about 250 kilometers for Amalthea. They orbit close to Jupiter, well inside the orbits of the famous Galilean moons. Their gravity is weak, but it's enough to exert resonant control over ring particles. Think of them as cosmic traffic cops, keeping everything moving in orderly lanes. Now imagine inserting a new, much more massive object into that system on a retrograde orbit. Retrograde is critical here because it means the object is moving opposite to the direction of Jupiter's rotation and opposite to the orbits of all the inner moons. When you have two objects on intersecting orbits moving in opposite directions, the relative velocities are huge. Encounters are violent. Gravitational perturbations are maximized. If 3I Atlas captured into a retrograde orbit that brought it anywhere near the inner moon system, the effects would compound over time. Each passage near a shepherd moon would tug on that moon's orbit slightly. The moon's velocity would change by tiny amounts, its orbital energy would shift, its distance from Jupiter would creep inward or outward. These changes would be small at first, but orbits are coupled systems. When one moon's orbit changes, it affects the resonances with other moons and with the ring particles. What starts as a tiny perturbation grows through feedback loops until the entire configuration becomes unstable. Let me walk you through a hypothetical disruption cascade. 3i Atlas settles into an elliptical retrograde orbit with a periapsis, or closest approach to Jupiter, that passes through or near the inner satellite region. Over weeks or months, repeated close approaches begin destabilizing the orbits of moons like Meti and Adrastea. Their orbits become more eccentric, their positions less predictable. Eventually, one of these moons crosses paths with another moon, or experiences tidal forces from Jupiter that exceed its structural strength. Tidal forces are brutal. If a moon gets too close to Jupiter, the difference in gravitational pull between the near side and far side can literally rip the moon apart. So now you have fragments, pieces of what used to be a moon, tumbling in chaotic orbits. These fragments collide with other fragments, grind against each other, and create vast clouds of debris. The ring particles which were being shepherded by the now destroyed or displaced moons lose their confinement. They begin to spread radially outward and inward. Some fall into Jupiter's atmosphere and burn up. Others migrate outward, forming a much wider, more diffuse ring system. And the whole time, more collisions are happening, more dust is being generated, creating a cascade effect where the ring system transforms from a faint set of confined bands into a bright, chaotic debris disk. This would be visible from Earth. Unlike Jupiter's current subtle rings, a disrupted ring system would scatter sunlight strongly. Depending on the amount of debris and how it's distributed, Jupiter could develop a halo visible even in amateur telescopes. Professional observatories would see it immediately. The ring would appear bright in reflected sunlight and warm in the infrared from absorbed heat. Over months or years, as the dust settles into new configurations, the appearance would evolve. It might look like a mini version of Saturn's rings at first, or it might be more irregular and patchy. Either way, it would be one of the most dramatic planetary changes in recorded history. Think about that for a second. Jupiter, the king of planets, suddenly sporting a ring system bright enough to see from your backyard. That's not just a scientific event, that's a cultural moment. People who barely pay attention to astronomy would notice. The night sky would look different. Now, the big caveat. This scenario depends heavily on the mass and orbit of 3i Atlas. If the object is low mass and settles into a distant, highly elliptical orbit that rarely comes near the inner moons, it might not cause any significant disruption at all. Jupiter's gravitational influence is so dominant that a small object in a wide orbit would be a negligible perturbation. The moons and rings would barely notice it was there. In that case, 3i Atlas would just become another one of Jupiter's dozens of small, irregular satellites. Interesting for scientists, but not visually spectacular. But if the mass is higher than expected, or if the orbit happens to be resonant with key moons, or if 3i Atlas's trajectory takes it through the ring plane repeatedly, then all bets are off. The system could destabilize surprisingly quickly. Orbital mechanics is full of situations where small changes lead to dramatic outcomes. This is one of them. There's historical context to consider as well. We know that moons collide and rings form through violent processes. Saturn's rings might have originated from a moon that was destroyed by tidal forces or a massive impact. Jupiter's current rings are thought to be continuously replenished by micrometeorite impacts on the inner moons. The solar system has a long history of catastrophic events reshaping planetary systems. What we're describing isn't unprecedented, it's just something that hasn't happened during human recorded history, yet. From a scientific standpoint, witnessing such an event would be invaluable. We'd get to study ring formation and moon dynamics in real time. Planetary scientists would have a natural laboratory for testing theories about how rings evolve, how debris cascades propagate, how gravitational interactions play out on observable timescales. The data would fill textbooks. But from a human perspective, it would also be deeply unsettling. Jupiter has looked the same for as long as our species has been watching the sky. Seeing it change would remind us that the solar system is not static. It's dynamic, violent, and indifferent to our expectations. So that's the physical scenario. 3i Atlas captures, possibly disrupts the ring system, turns Jupiter into a more spectacular but also more chaotic place. But beyond the science, beyond the physics, there's a whole other dimension to this story. If an interstellar object parks itself at Jupiter, humanity isn't going to just sit back and observe. There will be consequences, reactions, scrambles for advantage. The political and strategic implications might be even more disruptive than anything happening to Jupiter's moons. Because if 3i Atlas stays, it won't just be humanity's first permanent interstellar visitor. It might be our first alien artifact, and that changes everything about who we think we are and what we think we can claim. Buckle up. We're about to talk about why Jupiter might become the perfect alien outpost and what that means for us. Part 6. The High Ground. Hypothesis. Why Jupiter is the perfect alien outpost. Let's engage in a thought experiment. Imagine you're an advanced civilization with the ability to send probes across interstellar distances. You want to study a star system, maybe our star system specifically. Where do you park your observation platform? You could put it in the inner system, near Earth or Mars. That gets you close to the potentially inhabited worlds, but it's also risky. You're in the middle of the action, exposed to solar radiation, detectable by anyone with halfway decent telescopes. The environment is crowded with planets, asteroids, and increasingly human spacecraft. Not ideal for long-term covert observation. You could park in the outer system, maybe in the Kuiper belt beyond Neptune. That gives you isolation and safety. But you're also extremely far from anything interesting. Communication delays are long. Maneuvering takes time. You're essentially on the edge of the system, watching from a distance. Or you could choose Jupiter, and from a strategic standpoint, Jupiter makes a lot of sense. Let's start with the gravitational advantages. Jupiter contains more mass than all the other planets in the solar system combined. Its gravity well is enormous. If you're trying to establish a stable, long-term orbit, Jupiter offers the best anchor. Capture is difficult, yes, but once you're caught, you're not going anywhere without a lot of effort. Your orbit becomes part of the Jupiter system's architecture, stable over millions of years. That's valuable for a probe designed to last. Jupiter is also positioned perfectly. It's far enough from the Sun to avoid excessive radiation and heat, but not so far that you lose visibility of the inner system. From Jupiter, you can observe Earth, Venus, Mars, all with reasonable fidelity. The orbit also gives you a commanding view of the asteroid belt and the outer planets. It's the gravitational high ground of the solar system. In military terms, controlling the high ground gives you strategic advantage. Better lines of sight, easier defense, ability to dictate engagements. In space terms, Jupiter is that high ground. Then there's resources. Jupiter is mostly hydrogen and helium, with traces of methane, ammonia, water vapor, and other compounds. If you have technology capable of scooping atmospheric gases, Jupiter is a giant fuel depot. Hydrogen can be used for fusion propulsion. Helium is useful for cooling systems. Water can be split into hydrogen and oxygen for life support or propellant. A probe with refueling capability could use Jupiter as a resupply station, enabling missions deeper into the system or back out into interstellar space. You essentially have unlimited fuel if you can harvest it. There's also the magnetosphere. Jupiter's magnetic field is the strongest in the solar system, about 20,000 times more powerful than Earth's. This creates a massive magnetosphere that extends millions of kilometers into space. For a probe trying to shield itself from cosmic radiation, or trying to generate power through electromagnetic induction, or even trying to hide electromagnetic signatures, Jupiter's magnetosphere is incredibly useful. It's natural shielding and a potential energy source all in one. And then there's relative isolation combined with strategic position. The inner solar system is getting crowded. Humans have spacecraft around Earth, Mars, Venus, and several asteroids. Observatories are constantly scanning. But Jupiter? We've had a handful of flybys and one long-duration orbiter, Juno, which is focused on Jupiter itself rather than searching for anomalous objects in nearby space. A craft parked in orbit around Jupiter could go unnoticed for a long time, especially if it's small and designed to look like a natural satellite. By the time we detected it and recognized it as anomalous, it might have been there for years. The analogy to military strategy is hard to ignore. Throughout human history, armies have sought choke points, high ground, positions that offer both defense and control over supply lines. In space, Jupiter functions as a choke point for the outer solar system. Any mission heading beyond Jupiter has to deal with Jupiter's gravity. Any large-scale movement of resources from the outer system to the inner system would be influenced by Jupiter's presence. If you wanted to monitor or control access to the outer solar system, Jupiter is where you'd position yourself. Now, what would an alien probe actually do at Jupiter? Speculation is free, so let's speculate. The obvious mission is observation. A probe could study the inner planets, particularly Earth, looking for signs of life, technology, civilization. It could monitor radio transmissions, detect atmospheric composition changes, watch for nuclear detonations or other high-energy signatures. It could be gathering data for its creators, whoever and wherever they are, transmitting findings back through some means we don't have the physics to detect yet. Alternatively, the probe might be involved in resource harvesting, scooping Jupiter's atmosphere, extracting valuable materials, perhaps preparing for some larger operation we can't imagine. Or it could be a way station, part of a network of probes scattered across the galaxy, each monitoring a different star system, forming a vast observation grid. Or it could be dormant, waiting for some signal or condition to activate. The possibilities are endless because we have no idea what the motivations or capabilities of an interstellar civilization would be. Here's where recent scientific work adds legitimacy to the capture scenario. Studies published in 2025 have shown that interstellar objects can, under certain dynamical conditions, be captured by giant planets. The simulations use realistic models of solar system architecture and incoming ISO trajectories. They find that Jupiter is by far the most effective planet for capture because of its immense gravity. The captured objects typically end up on high eccentricity, inclined, sometimes retrograde orbits. In other words, exactly the kind of unusual orbit that 3i Atlas would have if it captured. This research shows that capture is not only possible, but perhaps even relatively common over the lifetime of a planetary system. So the alien outpost hypothesis isn't purely science fiction. The physics allows for it. The strategic logic supports it. And if 3i Atlas were designed with capture in mind, Jupiter is the obvious target. The question is whether it was chance or intent. Did 3i Atlas accidentally drift into a capture trajectory, or did it aim for Jupiter deliberately? Most scientists still believe 3i Atlas is a natural comet. Recent statements from mission scientists emphasize that all observations remain consistent with that interpretation. No techno-signatures have been detected. No radio emissions, no laser communications, no infrared heat anomalies suggesting internal power sources. By every measurable standard, it looks like a comet. But techno-signatures assume we know what to look for. If a civilization advanced enough to send probes between stars wanted to remain undetected, they probably could. Stealth in space is difficult but not impossible, especially over interstellar distances where observation assets are limited, and there's a psychological dimension here that's worth exploring. How would humanity react if we confirmed that an alien object was parked at Jupiter, not passing through, but staying? The discovery would redefine our place in the cosmos. For the first time, we'd have proof that intelligence exists beyond Earth, that technology exists capable of interstellar travel, and that we are being observed, or at least that our neighborhood is of interest to someone. The implications for religion, philosophy, politics, everything, would be staggering. Some people would feel awe, some would feel fear, most would feel both. And then there are the strategic and geopolitical consequences. If there's an alien probe at Jupiter, who controls access to it? Who gets to study it? Who benefits from any technology or knowledge it might contain? Those questions bring us to the next part of this story, the silent breakdown of the treaties and laws that are supposed to govern outer space. Because whatever legal framework exists now was written assuming celestial bodies are natural and uninhabited. An alien artifact changes the game completely. So while scientists and philosophers debate what it means, governments and militaries will be asking a different question. How do we get there first? Part 7. The Silent Treaty. Breakdown. Space law crumbles in real time. The Outer Space Treaty, signed in 1967 at the height of the Cold War, is the foundation of international space law. It's a document born from fear and hope in equal measure. Fear that the space race would lead to the militarization of orbit and nuclear weapons parked above our heads, and hope that space could remain a realm of peaceful exploration and scientific cooperation. The treaty has 5 key principles, but the one that matters most for our story is Article 2, which states that outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. In plain language, nobody owns the Moon, nobody owns Mars, nobody owns asteroids or comets or anything else beyond Earth. They belong to all of humanity, or they belong to no one, depending on how you interpret it. The treaty was designed to prevent nations from planting flags and claiming territory the way colonial powers carved up Earth, and for the most part it's worked. Governments have respected the principle, at least in letter, if not always in spirit. But the treaty was written with one big assumption, that celestial bodies are natural, inanimate, and unoccupied. What happens when that assumption breaks? If 3i Atlas captures at Jupiter and turns out to be artificial, the Outer Space Treaty doesn't really cover it. An alien probe isn't a celestial body in the natural sense. It's not a moon or asteroid formed by accretion and gravitational collapse. It's a manufactured object, possibly containing technology, materials, information. Does Article 2 apply? Can you claim you're not appropriating a celestial body because it's not actually a body but an artifact? Legal scholars would have a field day with this. Some would argue that the spirit of the treaty clearly intends to prevent any kind of appropriation in space, natural or otherwise. The goal is to keep space as a commons for all humanity. But others would argue that salvage rights apply to abandoned or derelict objects, and an alien probe with no evident operator present is legally speaking derelict. Whoever gets there first and establishes possession might have a claim, not of sovereignty but of salvage. That's a different legal framework entirely, more like maritime law than territorial law. Now, behind closed doors you can bet that governments are already having these conversations. Not publicly, because you can't publicly prepare for something that officially hasn't been confirmed. But in classified briefings, in back rooms at the United Nations, in legal advisory committees at space agencies, people are thinking through the implications. If 3i Atlas turns out to be a probe, and if a nation launches a mission to intercept it, what is the legal justification? How do you frame it so that you're not violating the Outer Space Treaty but also not letting some other nation get there first and claim salvage rights? One plausible argument: scientific research exemption. The treaty explicitly allows for the exploration and use of outer space for peaceful purposes and encourages international cooperation. A mission to study an alien probe could be framed as pure science. We're not claiming ownership, we're conducting research for the benefit of all humankind. Of course, in practice, whichever nation controls the mission also controls the data, the discoveries, the potential technology. But as long as you're not formally annexing the object, you might be within the legal bounds. Another argument: common heritage of mankind. This is a principle from the law of the Sea Treaty, applied to the deep ocean floor. The idea is that certain resources belong to all humanity collectively, and should be managed for everyone's benefit. You could argue that an alien artifact is the ultimate common heritage resource. It didn't come from Earth, so no nation has a prior claim. Therefore it should be governed collectively. But in practice, implementing collective governance is messy and slow, and in a first-come situation, the nation that arrives first de facto controls the artifact, at least temporarily. And then there's the urgency argument. If the probe is functional, if it's transmitting data, if it poses any kind of security risk, a nation might claim the right to intercept it on grounds of planetary defense or threat assessment. This stretches the treaty pretty far, but when the stakes are existential, legal niceties tend to fall by the wayside. History is full of examples where laws were reinterpreted or ignored when nations felt threatened or saw an opportunity too valuable to pass up. So picture this speculative scenario. It's late 2026. 3i Atlas has captured at Jupiter. Observations suggest it's not natural. Leaked analyses show trajectory, anomalies, compositional weirdness, maybe even structural features that don't match comet models. The information isn't public yet, but it's circulating among space agencies and intelligence services. Suddenly, multiple nations announce missions to Jupiter. They all claim scientific objectives. They all invoke the Outer Space Treaty's Peaceful Purposes Clause. But everyone knows what's really happening. A race to get there first, study the object up close, and if possible, salvage whatever technology or materials it contains. Alliances would form quickly. The nuclear-capable spacefaring nations, the United States, Russia, China, would be the primary actors. But other nations with advanced space programs, Europe through ESA, India, Japan, might push for involvement or launch their own missions. There would be back-channel diplomacy, secret deals, technology sharing agreements. Countries without the capability to launch might offer funding, data, or political support in exchange for access to findings. It would be the geopolitical equivalent of a gold rush. except instead of gold, the prize is potentially world-changing alien technology. The risks of this scenario are enormous. First, there's the precedent. If one nation successfully claims salvage rights or de facto control over an alien artifact, it sets a template for future encounters. Space law becomes whoever gets there first wins, which undermines the whole commons framework. Second, there's militarization. Even if the missions claim to be peaceful, the technology needed to reach Jupiter quickly, intercept an object, and potentially manipulate or retrieve it is dual use at minimum. Nuclear thermal propulsion, for example, is useful for fast interplanetary transit, but also has obvious military applications. The more nations develop these capabilities in a rush, the more unstable the security environment becomes. Third, there's the possibility of conflict. If two missions arrive at 3i Atlas at roughly the same time, what happens? Do they cooperate? Do they compete? Do they physically interfere with each other? Space is big, but orbits around Jupiter are a finite resource, and if multiple spacecraft are trying to position themselves near the same object, the risk of collision or hostile action increases. We've seen satellite near misses in Earth orbit. Imagine the same dynamics playing out at Jupiter with higher stakes and less oversight. Real-world tensions in space law offer a preview. Debates about asteroid mining have raised similar questions. If a private company lands on an asteroid and extracts resources, do they own those resources? The Outer Space Treaty says they don't own the asteroid, but US law, through the Space Act of 2015, says they can own the resources they extract. Other nations have passed similar laws. This creates a legal grey area where the treaty says one thing but national laws say another. The same kind of grey area would apply to an alien probe. The treaty says you can't appropriate it, but national law might say you can salvage it, study it, even dismantle it for analysis. And here's the most unsettling part. All of this could happen quietly. Treaties don't usually collapse in dramatic public ways. They erode through reinterpretation, selective enforcement, and precedents that accumulate until the original principles are unrecognizable. The Outer Space Treaty could remain technically in force, while being effectively meaningless because everyone has carved out their own exceptions and justifications. That silent breakdown might already be starting. We just don't see it yet because the triggering event, 3i Atlas's capture, hasn't happened. So the question becomes, if 3i Atlas is humanity's first alien asset, are we ready to treat it as a global commons, or will it become a prize to be claimed by whoever has the fastest rocket and the loosest interpretation of international law? And speaking of fast rockets, there's one technology that could change the timeline drastically: nuclear thermal propulsion. If any nation has NTP ready to launch, they could reach Jupiter in a fraction of the time it would take with chemical propulsion. That's a game changer. So who really has NTP capability right now, and how close are they to deploying it? Let's find out. Part 8. The Nuclear Thermal Gold Rush. Who really has NTP ready to launch? Chemical rockets are slow. That's the first thing you need to understand about the challenge of reaching Jupiter quickly. The Juno mission, which launched in 2011, took 5 years to reach Jupiter. The Galileo probe took 6 years. Even with gravity assists from Earth and Venus, the trip is measured in years, not months. For a typical chemical propulsion mission, you're looking at transit times of 5 to 7 years depending on the launch window and trajectory. That's fine for a leisurely scientific mission. But if there's an alien probe parked at Jupiter, and multiple nations racing to be the first to reach it, 5 years is an eternity. Enter nuclear thermal propulsion, or NTP. The concept is straightforward, but the engineering is complex. Instead of burning chemical fuel to create hot gas that shoots out the back of the rocket, you use a nuclear reactor to heat a propellant, typically hydrogen, to extreme temperatures. The superheated hydrogen then expands through a nozzle, producing thrust. The advantage is efficiency. NTP engines can achieve specific impulses, a measure of efficiency, roughly twice that of the best chemical rockets. That translates to either higher speeds for the same fuel mass, or less fuel needed for the same speed, or some combination of both. Bottom line, NTP can cut Jupiter transit times dramatically, potentially down to around 2 years or even less for high-energy trajectories. This isn't science fiction. Nuclear thermal propulsion has been studied since the 1950s. The United States ran the NERVA program in the 1960s and early 70s, which successfully tested nuclear rocket engines on the ground. The engines worked, the technology was proven, but the program was cancelled in 1973 due to budget cuts and the end of the Apollo era. Since then, NTP has been in a state of perpetual, we should really look into this again, with occasional resurgences of interest but no operational hardware. Until recently. In the last few years, interest in NTP has surged, driven in part by ambitions for crewed Mars missions, and in part by the recognition that chemical propulsion is a limiting factor for deep space exploration. DARPA, the Defense Advanced Research Projects Agency in the United States, launched a program called DRACO, Demonstration Rocket for Agile Cislunar Operations, aimed at developing and testing a nuclear thermal propulsion system. The goal is to demonstrate an operational NTP engine in orbit by the late 2020s. Other spacefaring nations, notably Russia and China, have also announced renewed interest in nuclear propulsion, though details are scarce. Here's where things get interesting. If 3I Atlas captures at Jupiter in March 2026, and if the object turns out to be anomalous enough to trigger a salvage race, the timeline for launching an intercept mission becomes critical. A chemical rocket launched in 2027 wouldn't arrive until 2032 or later. That might be acceptable if you're confident nobody else is going faster, but if a competitor has NTP and can reach Jupiter by 2029 or 2030, they win. First arrival is everything in a salvage scenario. Whoever gets there first controls the initial data, the narrative, and potentially the object itself. So the question is, who actually has NTP ready to go, or nearly ready, as of late 2025? The honest answer is that nobody has a fully operational flight-ready NTP system right now. The US DRACO program is promising, but it's still developmental. The planned in-space demo is years away, and even if successful, scaling up to a Jupiter mission would require additional time, funding, and probably political will that doesn't exist yet under normal circumstances. Russia has a long history of nuclear propulsion research, dating back to the Soviet era. But post-Soviet economic and political turbulence has slowed many of their advanced programs. China is secretive about its capabilities, which makes assessment difficult, but most analysts believe they're roughly on par with the US in terms of technology readiness, meaning developmental but not operational. However, context matters. If the stakes suddenly change, if 3I Atlas becomes a confirmed alien artifact, the calculus shifts. Projects that were underfunded or low priority become urgent. Black budgets expand, timelines compress. The history of technology development shows that when governments decide something is critical for national security or strategic advantage, things can happen fast. The Manhattan Project went from concept to operational nuclear weapons in under 4 years. The Apollo program put humans on the moon less than a decade after Kennedy's speech. If there's political will and funding, NTP could be accelerated significantly. A speculative but plausible timeline might look like this. Late 2026. 3I Atlas captures and initial assessments suggest it's not natural. Early 2027. Classified briefings to heads of state, emergency funding approved, crash programs initiated to accelerate NTP development. Mid-2027. First launches of precursor missions using existing technology, basically chemical propulsion spacecraft that will take years to arrive but secure a claim and begin preliminary observations. Late 2027 to early 2028. If NTP programs hit their milestones, assembly of crewed or uncrewed NTP-powered missions begins. Launch window targeting late 2028 or 2029. Arrival at Jupiter around 2031 or 2032. That's tight. Very tight. It assumes everything goes right, no major technical failures, no political obstacles, perfect coordination between agencies that normally don't coordinate well. But it's not impossible. The incentive structure is there. The nation that reaches 3I Atlas first and returns with data, samples, or technology gains an advantage that could reshape geopolitics for generations. That's not hyperbole. If the probe contains any kind of advanced propulsion, materials science, computing, or energy generation technology, reverse engineering it could leapfrog terrestrial tech by decades or centuries. The economic and military value would be incalculable. And let's talk about the hazards, because NTP is not without serious risks. First, there's the obvious radiation issue. Nuclear reactors produce radiation, and while you can shield the crew and sensitive equipment, there's always risk. If something goes wrong during launch or operation, You could have radioactive material dispersed in Earth orbit, or worse, re-entering the atmosphere. Public opinion on nuclear technology in space is mixed at best, and a high-profile accident could derail the entire effort. Second, there's the political blowback. Treaties governing nuclear materials in space exist, specifically the Outer Space Treaty's prohibition on placing nuclear weapons in orbit. NTP is not a weapon, but it uses nuclear reactors, and the line between propulsion and potential weaponization is uncomfortably thin. Other nations might view an NTP-powered mission as a precursor to militarization, triggering arms race dynamics. Diplomatic fallout could be severe. Third, there's the environmental impact. Space debris from nuclear-powered missions could contaminate orbits or create hazards for future missions, and if a mission fails and the reactor ends up in Jupiter's atmosphere or on one of its moons, you've just introduced radioactive material into an environment scientists have tried to keep pristine for astrobiological reasons. But despite all these hazards, the pressure to deploy NTP in a crisis scenario might override caution. History is full of examples where strategic necessity trumps safety and environmental concerns. The Cold War space race involved plenty of risks that seem reckless in hindsight. If the prize is an alien probe, many governments would decide the risks are worth it. The comparison to historical resource grabs is apt. The California gold rush saw people abandoning everything to chase wealth, often with inadequate preparation and little regard for consequences. The scramble for oil in the early 20th century reshaped global politics and led to conflicts that still resonate today. Colonial-era land grabs by European powers were driven by the same logic. Get there first, claim what you can, worry about morality and legality later. Space, particularly around an alien artifact, could become the next wild frontier where the old rules don't quite apply and new rules haven't been written yet. And while governments fight over launch schedules and legal interpretations and who has the best rocket, there's another battle happening quieter but no less important. The scientific community is fracturing over how to interpret 3I Atlas. Some see a comet, some see an anomaly, some see whatever they want to see. The data wars are intensifying, and information is being controlled, disputed, and weaponized by people who are supposed to be on the same side. Let's talk about that. Part 9. The fractured scientific community and the data wars. Science is supposed to be about consensus built on evidence. You make observations, you publish results, your peers review the work, and slowly a consensus emerges about what the data actually shows. That's the ideal. But ideals don't always survive contact with reality, especially when the reality in question might be an alien probe, and the stakes involve national prestige, funding battles, and the potential rewriting of humanity's place in the universe. The official scientific consensus on 3I Atlas, as of late 2025, is clear. Leading observatories and space agencies describe it as behaving like a comet. Observations show a nucleus, a coma, tails composed of gas and dust. Spectroscopic analysis reveals water, carbon dioxide, carbon monoxide, organic compounds, all consistent with cometary composition. The object's brightness varies with rotation, which matches models of an irregular nucleus tumbling through space. No radio signals have been detected, no artificial structures resolved, no technosignatures identified. By every standard measure, 3I Atlas is a comet, albeit an interstellar one, which makes it interesting but not revolutionary. That's the official line. But in online forums among amateur astronomers, and even in private conversations among some professional researchers, there's growing skepticism. Not about the data necessarily, but about the interpretation and, in some cases, about what data is being shared publicly versus what might be kept internal. Claims have circulated, unverified but persistent, that early observations of 3I Atlas showed features or behaviour that didn't fit comet models, and that these observations were either downplayed or retracted. One story involves a telescope team that initially reported unusual symmetry in the coma, or an unexpected spike in brightness that couldn't be explained by standard outgassing. According to the rumour, which I want to emphasise is unverified, the team was told to reanalyse the data, or the observation was attributed to instrumental error. Maybe it was instrumental error. Telescopes produce artefacts all the time. But the perception among some observers is that inconvenient data gets buried. Then there are rival data sets. Professional observatories have strict protocols for data release, peer review, and publication. But amateur astronomers with good equipment can capture images and spectra of bright comets too. In some cases, amateur data has shown tail structures or jet directions that don't quite match the published professional observations. Are these differences real, or are they due to differences in observation angle, timing, or equipment sensitivity? Probably the latter. But when you have a subset of the community convinced they're seeing something important that's being ignored, those differences feed suspicion, and there are accusations, more like insinuations really, of censorship or gatekeeping. Some claim that major observatories are reluctant to publish anything that makes 3i Atlas look too anomalous because they don't want to fuel speculation or cause public panic. Others suggest that government-affiliated agencies are applying pressure to keep interpretations conservative until more data is available, basically a wait-and-see approach to avoid premature conclusions. These claims are hard to evaluate because scientific institutions do sometimes move cautiously, and that caution can look like suppression even when it's just prudence. Now, recent scientific publications do complicate the picture in interesting ways. The preprint on galactic cosmic ray processing that we talked about earlier found that 3i Atlas has extremely high ratios of carbon dioxide to water and substantial carbon monoxide, much more than typical solar system comets. The outer layers appear to have been heavily processed by cosmic radiation over millions of years. This processing produces organic-rich, carbon dioxide-rich crusts that behave differently from fresh comet ice. The paper is careful to frame these findings as consistent with an interstellar origin and long-duration exposure to the interstellar medium, not as evidence of anything artificial. But it does show that 3i Atlas is chemically unusual compared to the comets we're familiar with. What does that mean? If you're a mainstream scientist, it means interstellar comets are different from solar system comets, because they've experienced different environments. It's a natural outlier, interesting precisely because it's giving us a look at how objects evolve over interstellar timescales. If you're more speculative, you might wonder whether the processed crust could be hiding something underneath, or whether the unusual chemistry makes the object harder to categorize definitively. There's also a social dimension to how scientists deal with outliers. The history of science is full of cases where anomalous data was initially dismissed because it didn't fit prevailing theories, only to later be recognized as important. Continental drift, the impact theory of dinosaur extinction, even the existence of meteorites was once disputed. Scientists are trained to be skeptical, which is good, but sometimes skepticism slides into conservatism, where anything that challenges the consensus is treated with extra scrutiny, while conventional interpretations get a pass. This is human nature, not malice, but it affects how data is interpreted and communicated. And then there's the public and amateur side. Online forums dedicated to comets and asteroids have been buzzing with discussions of 3i Atlas since its discovery. Some observers claim to see structure in the coma, asymmetries that suggest non-random processes, like curve variations that don't match simple rotation. Detailed spectral analysis by hobbyists, or at least people claiming to have done spectral analysis, has identified what they call anomalous emission lines, or unusual ratios of elements. Are these observations valid? Some might be. Others are probably misinterpretations or artifacts. But the volume of claims creates a narrative that mainstream science is missing something, or refusing to engage with alternative interpretations. The communication challenge here is enormous. If you're a scientist trying to do careful, rigorous work, you don't want to feed speculation by prematurely announcing that something is weird. You want to triple-check your data, rule out instrumental effects, get peer review. But that caution creates a vacuum that gets filled with speculation and conspiracy theories. Meanwhile, if you're a member of the public who's been told for years that science is about open inquiry and following the evidence wherever it leads, and you see data that suggests anomalies being met with, "it's probably nothing," you might start to distrust the official narrative. This schism matters because if we can't trust consensus, we end up with multiple competing realities. Some people believe 3i Atlas is just a comet. Some believe it's something more, and depending on which version you accept, your expectations for March 2026 are radically different. If it's a comet, the close approach will be a nice observing opportunity, maybe some good data for comet scientists, and then it's gone. If it's something else, March 2026 could be a turning point in human history. The irony is that both groups want the same thing, to understand what 3i Atlas really is. But the process of getting to that understanding is messy, contested, and increasingly politicized. Data is supposed to be objective, but data interpretation is inherently subjective, shaped by assumptions, training, and sometimes by incentives that have nothing to do with truth. And that brings us to the most provocative question of all. Setting aside institutional politics and data disputes for a moment, let's look purely at the mechanics. Could 3i Atlas actually be piloted? Are there patterns in its motion, signatures in its trajectory that suggest some form of control? Because if there are, that changes everything. Part 10. The final mystery. Why every model suggests Atlas behaves like it's being piloted. Let me lay out a scenario that a small number of analysts have been quietly discussing, usually in private because saying it out loud sounds ridiculous. They've been looking at the trajectory of 3i Atlas, not just the overall path, but the fine details, the microscale variations, and some of them see patterns, small course adjustments that happen at suspiciously convenient times, velocity changes that correlate with external perturbations in ways that seem too precise to be random outgassing. They see, in other words, behavior that looks less like a comet tumbling passively through space and more like something making decisions. This claim is speculative and unproven. Let me state that clearly up front. No peer-reviewed paper has definitively established that 3i Atlas is under intelligent control. The analysts making these claims are, in some cases, working independently, outside mainstream institutions, using publicly available data. They could be wrong. They could be seeing patterns that aren't there. The human brain is wired to find patterns even in randomness. But their arguments are interesting enough that we should at least consider them seriously. The basis for the piloting hypothesis comes from trajectory fitting. When you track an object's motion, you start with a gravitational model. The sun's gravity, planetary perturbations, relativistic effects, all the things that affect orbits. Then you add non-gravitational forces to account for deviations, solar radiation pressure, comet outgassing, drag from interplanetary dust, whatever might apply. For most comets, once you include outgassing in a reasonable way, the model fits the observations well. The residuals, the differences between prediction and observation, are small and random. For 3i Atlas, some analysts claim the residuals aren't quite random. They point to moments when the object's velocity changed by tiny amounts, on the order of meters per second or less, at times when you'd expect perturbations from external sources like solar wind pressure variations or close approaches to minor planets. The odd thing is that the velocity changes seem to compensate for those perturbations, keeping the object on a more stable long-term trajectory than you'd expect from passive dynamics. It's like the object is anticipating disruptions and correcting in advance. This is what they call anticipatory correction or predictive maneuvering. To make this work, the object would need sensors to detect external forces, some kind of computational or mechanical system to calculate corrections, and a propulsion mechanism to execute them. That sounds like a spacecraft, not a comet. But here's the problem. How would you distinguish anticipatory correction from just really well-timed outgassing? Comets do have jets that fire based on solar heating, and those jets can produce thrust in specific directions. If a comet's rotation and surface features happen to align such that jets fire at convenient times, it could mimic control without actually being controlled. The counter-argument from mainstream astronomy is exactly that. Asymmetric outgassing, they say, can produce complex motion. Rotational dynamics of an irregular nucleus can make jets turn on and off in patterns that look organized but are actually just physics. There's no need to invoke intelligence. Natural processes are sufficient to explain the observations, and crucially, no direct evidence of technosignatures has been found. No radio emissions, no infrared anomalies suggesting onboard power generation, no resolved structure that looks artificial. By Occam's razor, the simplest explanation is a natural comet, and that's what we should accept until proven otherwise. Fair point. But let's explore the alternative for a moment. If 3i Atlas were being piloted, why? What would be the motive? One possibility is positioning. If the object's mission is to enter orbit around Jupiter, it needs to arrive with precisely the right velocity and trajectory. Too fast and it flies past. Too slow and it might crash or get perturbed onto an unstable path. Executing small corrections during the approach phase would ensure it hits the target. This is exactly what spacecraft do. Mission controllers fire thrusters periodically to correct trajectory errors and keep the spacecraft on course. An automated probe could do the same using onboard systems. Another possibility is that the object is trying to avoid detection. By making only tiny, infrequent adjustments, it minimizes the chances of triggering anomaly alerts in tracking systems. Large sudden maneuvers would be obvious. But if you change velocity by a few meters per second every few weeks, timed to coincide with natural activity like outgassing bursts, you can stay under the radar. Most tracking systems would attribute the changes to comet activity and not flag them as unusual. Or maybe the object is gathering data. Each small maneuver could be adjusting its orientation or trajectory to optimize observations of specific targets. Earth, the asteroid belt, Jupiter's moons. A passive comet doesn't care where it's pointed, but a probe with instruments would. Small corrections could be about maximizing mission return rather than just staying on course. These are all hypotheticals, but they illustrate that if you assume the object is piloted, there are plausible operational reasons for the behaviors being claimed. The question is whether those behaviors are real or imagined. There's also the issue of propulsion. How would 3i Atlas maneuver? One suggestion is that if it's artificial, it could have a low-thrust engine, maybe ion drive or something more exotic, that produces tiny amounts of thrust over long periods. Such an engine wouldn't be detectable from Earth because the exhaust would be too faint and dispersed. Alternatively, if the object has a volatile-rich outer layer, it could use controlled outgassing as a propulsion method, essentially turning its comet disguise into a functional thruster. Heat specific regions to release gas in specific directions. It's inefficient but effective and completely undetectable as artificial. The lack of confirmed technosignatures is the strongest argument against the piloting hypothesis. If there's an engine, there should be heat. If there's computation, there might be electromagnetic emissions. If there's structure, we should see it in high-resolution images. Hubble has imaged 3i Atlas, so have ground-based adaptive optics systems. Nobody has reported seeing anything that looks like a spacecraft. All the images show a point source with a diffuse coma, exactly what a comet should look like. But here's the thing about technosignatures. They assume the technology is recognizable. If an advanced civilization designed a probe to be stealthy, to blend in with natural objects, it would be covered in comet material. The engines might be shielded or only operate in ways that mimic natural processes. The computing might be done with systems that don't emit radio frequencies, or that emit in bands we're not monitoring. We tend to think of alien technology as shiny and obvious, but maybe that's naive. Maybe advanced technology is subtle and mimetic, designed to look like nothing special until you inspect it up close. So where does that leave us? With a set of claims about anomalous trajectory behavior that are unproven and contested. With a mainstream scientific consensus that 3i Atlas is a comet and nothing more. And with a nagging uncertainty that won't go away because the data, while consistent with a comet, doesn't definitively rule out something else. If 3i Atlas is piloted, who or what is behind it? That's unknowable with current data. An alien probe from another star system is the obvious guess, but it could also be something we haven't imagined. What's its mission? Observation, probably, if it exists at all. Why now? Maybe coincidence, or maybe there's something about this moment in Earth's history, our level of technological development, that makes observation worthwhile. And those questions lead us out of the immediate technical details and into the wider cosmic context. Because 3i Atlas isn't happening in isolation. It's part of a broader shift in how we think about interstellar visitors, how we model the solar system's interaction with the galaxy, and how we search for intelligence beyond Earth. The science around these topics has been evolving rapidly in 2025, and some of the new findings are almost as wild as the idea of a captured alien probe. Let's zoom out and look at the bigger picture. Part 11, 2025, Aerocapture Studies, the growing realization that interstellar objects might be more common. For a long time, astronomers assumed interstellar objects were rare. The detection of 1I/Oumuamua in 2017 was treated as a once-in-a-career event. The discovery of 2I/Borisov in 2019 confirmed that ISOs existed and could be detected, but still, 2 objects in a few years suggested we might see 1 every couple of years at best. The solar system in this view was relatively isolated, with only occasional intruders from the wider galaxy drifting through. That view is changing. New research published in 2025 has shown that not only are interstellar objects more common than we thought, but some of them don't leave. They get captured. And if the models are right, there could be dozens or even hundreds of captured interstellar objects orbiting the Sun or orbiting giant planets right now, invisible to our surveys because they're dark, distant, and indistinguishable from native solar system bodies. The key study, titled something like Capture of Interstellar Objects and Binaries, used N-body simulations to model how ISOs interact with the solar system over millions of years. The simulations start with a steady stream of ISOs entering the solar system from random directions at interstellar velocities. Most pass through and leave, just like 1I/Oumuamua did. But a small fraction encounter planets, especially Jupiter, at just the right angle and velocity to lose enough energy that they become gravitationally bound. The capture process usually involves a close approach to Jupiter, sometimes multiple approaches as the object gets pulled into a chaotic resonance, until it settles into a stable, highly eccentric orbit. The simulations found that over the age of the solar system, roughly 10 ISOs could currently be in bound orbits. These objects would have high eccentricities, large inclinations relative to the ecliptic plane, and some would be in retrograde orbits. Their orbital periods could be thousands, or even millions of years, taking them far from the Sun for most of their orbits. When they're distant, they're cold, dark, and nearly impossible to detect with current telescopes. We might have passed them in catalogues of asteroids or comets without recognizing them as interstellar. This is a profound realization. It means the solar system is not a closed ecosystem, it's porous. Objects leak in from interstellar space, and at least some of them stay. We're not just being visited occasionally, we're accumulating visitors. Over billions of years, that accumulation could be significant. Some of those captured ESOs might even have played roles in solar system history, delivering volatiles to the inner planets, impacting Earth or the Moon, contributing to the chemical inventory that made life possible. The study specifically highlights Jupiter as the most effective capture agent. Its massive gravity well and its position in the outer solar system make it the ideal place for ISOs to lose velocity and become trapped. Saturn, Uranus and Neptune can capture objects too, but less efficiently. The models suggest that most captured ISOs are either in orbits around the Sun with Jupiter-like periods, or they're actually in orbit around Jupiter itself, becoming irregular moons. And here's where 3I Atlas fits in. If it captures in March 2026, it wouldn't be a fluke. It would be part of a natural process that's been happening for the entire history of the solar system. The difference is that this time, we're watching it happen in real time with telescopes and spacecraft. We can study the capture process, measure the orbital changes, potentially even visit the object afterward. That's unprecedented. But it also raises questions. If there are other captured ISOs out there, why haven't we found them? Part of the answer is that we haven't been looking in the right ways. Most asteroid and comet surveys focus on objects that are bright and active. A dormant ISO, cold and inert, would be invisible unless it happened to pass close to Earth, or reflects sunlight at just the right angle. Another part of the answer is that we might have found them and not recognized them. The catalogues of known minor planets include thousands of objects with unusual orbits. Some of those could be captured ESOs misidentified as native objects. It would take detailed spectroscopic analysis and trajectory studies to distinguish them, and that work hasn't been done systematically. There could be weird, unexplained objects in the existing catalogues that are interstellar immigrants, high-inclination asteroids with strange compositions, long-period comets that don't quite fit formation models, irregular moons of Jupiter and Saturn that look like captured bodies but are assumed to be solar system natives. Re-examining these objects with an ISO hypothesis in mind could reveal surprises. The implications for planetary science are significant. If captured ISOs are common, they provide natural laboratories for studying the compositions and structures of objects from other star systems. Each one is a sample of material that formed in a different environment around a different star, possibly with different chemistry and isotopic ratios than solar system bodies. Studying them could teach us about exoplanet systems, stellar evolution, galactic chemical evolution, all from samples that came to us rather than requiring interstellar missions to retrieve. And philosophically, this changes how we think about the solar system. It's not an isolated island in space. It's more like a train station where interstellar travelers arrive, some pass through, and some stay. The boundaries are fuzzy. The definition of what belongs here and what doesn't becomes ambiguous. 3I Atlas, if it captures, becomes part of the solar system's extended family. a permanent reminder that we're connected to the wider galaxy whether we like it or not. That connection brings us to another recent development. If captured ISOs are common, and if they've been modified by interstellar conditions during their journeys, what do they actually look like when they arrive? New research on cosmic ray processing gives us some answers, and those answers are strange. Part 12, 20, 25, Cosmic Ray Processed Nuclei, a new model for interstellar objects. Interstellar space is not empty. It's filled with gas, dust, and high-energy particles called cosmic rays. These particles, mostly protons and atomic nuclei, zip through the galaxy at speeds approaching the speed of light. They're produced by supernova explosions, active galactic nuclei, and other violent astrophysical processes. When cosmic rays hit solid matter, they pack enough energy to break chemical bonds, ionize atoms, and rearrange molecular structures. Over long timescales, this bombardment can fundamentally alter the surface chemistry of an object. For most solar system bodies, cosmic ray exposure is limited. They spend their time within the sun's magnetic field, which deflects most galactic cosmic rays. But an object traveling through interstellar space for millions of years has no such protection. It's exposed to the full flux of galactic cosmic rays constantly. The cumulative dose is enormous, and the chemical consequences are significant. A preprint published in 2025 analysed the spectral data from 3I Atlas and concluded that its surface has been heavily processed by cosmic rays. The evidence comes from the composition. The ratios of carbon dioxide to water and carbon monoxide to water are among the highest ever measured for any comet. These ratios can't be explained by primordial composition alone. Something has converted water ice and simple carbon-bearing molecules into carbon dioxide and more complex organics. Cosmic ray bombardment can do exactly that. Here's how it works. Cosmic rays strike the surface, transferring energy to the molecules. Water ice, H2O, can be dissociated into hydrogen and oxygen. The hydrogen escapes because it's light, but the oxygen stays and can react with carbon-bearing molecules to form carbon dioxide, CO2. Carbon monoxide, CO, is more stable under radiation than water, so it accumulates preferentially. Over millions of years, the surface layer becomes enriched in CO2 and CO relative to water. Organic molecules, chains of carbon, hydrogen, oxygen, and nitrogen also form through radiolysis, the breaking and recombining of molecules by radiation. The result is a crust that's chemically distinct from the interior. The outer 15 to 20 meters of 3I Atlas's nucleus might be this processed layer, rich in carbon dioxide, organics, and refractory material that's harder to sublimate than fresh ice. Underneath, there could be more pristine material, closer to the original composition. But we can only observe what's outgassing from the surface, so we're seeing the processed layer, not the interior. This processed crust has several implications. First, it affects outgassing behavior. A crust rich in organics and CO2 might be less volatile than water ice, requiring more solar heating to sublimate. That could explain why 3I Atlas's coma and tails don't match typical comet models perfectly. The gas release might be delayed or less intense than expected for a fresh comet. Second, the crust might be structurally harder, more compacted than fresh comet material. Cosmic ray processing could create a kind of hardened shell that insulates the interior and changes the object's mechanical properties. And third, if the crust is hardened, it might survive atmospheric entry better than a fluffy comet would. This is relevant to the aerocapture scenario. A comet with a soft, porous structure would likely disintegrate if it dipped into Jupiter's atmosphere at high speed. But a comet with a tough, processed crust might hold together long enough to complete the maneuver. That increases the feasibility of capture, at least in cases where atmospheric drag is involved. The broader implication is that all interstellar objects we detect are probably weathered relics, not pristine samples. 1I/Oumuamua, 2I/Borisov, 3I Atlas. They've all been travelling through interstellar space for possibly millions of years, getting bombarded by cosmic rays, accumulating damage, changing chemically. What we observe when they arrive is the end state of that process, not the original object. To understand their true nature, we'd need to account for this processing and extrapolate backward, which is difficult. This complicates efforts to study interstellar objects as proxies for exoplanet system compositions. If the surfaces are all heavily modified, can we trust the spectral data to tell us about the star system they came from? Maybe. The isotopic ratios might still be primordial, and some refractory elements wouldn't be affected by cosmic rays. But the volatile inventories, the organics, the ice compositions, all of those could be products of interstellar processing rather than formation conditions. There's also a weird side effect of cosmic ray processing that's worth mentioning. The organic-rich crusts could, in principle, be more dense than fresh ice. Compacted organics have densities closer to 1 gram per cubic centimetre, or higher, compared to fluffy ice at 0.5. If the outer layer of 3I Atlas is a compacted organic-rich crust, that could contribute to the mass problem we discussed earlier. It's not a metal core, but it's denser than you'd expect for a normal comet, and that density difference might be enough to explain some of the gravitational anomalies claimed by observers. The 2025 compositional study is the first of its kind to really dig into cosmic ray processing effects in detail. As more interstellar objects are discovered and studied, we'll learn whether 3I Atlas is typical or unusual among ISOs. If all ISOs show heavy processing, that becomes the new normal. If 3I Atlas is an outlier even among processed ISOs, that's interesting in a different way. But while we're grappling with how cosmic rays alter objects over eons, other parts of the solar system are showing us that things can change on much shorter timescales. In fact, something odd happened recently in the outer solar system that reminded astronomers how little we understand about even our own neighbourhood. Let's talk about that. Part 13, April 2025. The sudden brightening of a far Kuiper object. In April of 2025, astronomers observing distant Kuiper belt objects noticed something unexpected. One particular object, a small body orbiting in the cold outer reaches of the solar system beyond Neptune, suddenly became brighter. Not by a little, but by enough that it was clearly detectable in multiple wavelengths. The change happened over a few days, then the brightness seemed to stabilize at the new, higher level. As of late 2025, the object is still brighter than it was before the event, and nobody is entirely sure why. Kuiper belt objects are usually static. They're cold, dark and unchanging on human timescales. They've been in stable orbits for billions of years, far from the sun's heat, barely affected by anything except the occasional distant gravitational tug from Neptune. When one of them suddenly changes brightness, it demands an explanation. The leading hypothesis for this particular event is some kind of surface change. Maybe a layer of dark material sublimated or was blown off, exposing brighter, more reflective ice underneath. This could happen if the object has internal heat sources, perhaps from radioactive decay or tidal friction if it's part of a binary system. Another possibility is cryovolcanism, where subsurface volatiles escape and coat the surface with fresh frost. Cryovolcanism is known to occur on Enceladus, one of Saturn's moons, and on Triton, Neptune's largest moon. It's plausible that some Kuiper belt objects have similar activity. A third possibility is an impact. If a small impactor, maybe a rogue asteroid or another Kuiper belt object on a crossing orbit, hit the target, it could have kicked up subsurface material and created a temporary cloud of debris that reflects more light. Over time, that debris would settle or disperse, and the brightness would return to normal. But in this case, the brightness hasn't returned to normal yet, which suggests the change is more permanent, like a surface alteration rather than a transient event. And then there's the exotic hypothesis, external illumination or radiation. What if something in the outer solar system is emitting energy that heats or illuminates Kuiper belt objects in unexpected ways? This sounds far-fetched, but we're discussing it in a context where we're already talking about alien probes and captured interstellar visitors. If there's unusual activity happening in the outer solar system, could it be connected? Is 3I Atlas not the only anomalous object? Are there other things going on that we're not noticing because we're focused on the obvious targets? That's speculative to the point of wild conjecture. But the broader point is valid. The solar system is more dynamic than we often acknowledge. Things change. Objects that should be inert show activity. Processes we thought were limited to active bodies like comets turn out to occur on distant, supposedly dead worlds. The outer solar system in particular is a frontier where our observations are sparse and our understanding is incomplete. If the outer solar system is more active and more volatile than we assume, Maybe interstellar visitors or captured objects aren't the only anomalies. Maybe we're miscategorizing lots of objects. Maybe the line between natural and artificial isn't as clear as we think, because natural processes can produce behaviors that look designed, and designed objects can mimic natural processes. This shifts the perspective. Instead of seeing 3i Atlas as a singular, isolated mystery, we start to see it as part of a larger pattern. The solar system is full of things we don't understand. Brightening Kuiper Belt objects, captured interstellar immigrants, comets with anomalous compositions, moons with unexpected geology. Each individual case can be explained away with enough effort, but collectively they suggest that our models are missing something, and that something might be that the universe is weirder than our theories allow. Not alien probe weird necessarily, but weird in ways that challenge the assumptions we've built our understanding on. The assumptions that objects are simple, that processes are predictable, that what we see is what's there. Sometimes what we see is not what's there, because we're not looking closely enough, or because the thing we're looking at is designed not to be seen clearly, or because our instruments and methods are tuned for the expected and miss the unexpected. This leads into a broader question that's been simmering in the scientific community for a while. Are we ready to seriously consider technosignatures, not just as a SETI radio search problem, but as something that could show up in our astronomical data? In 2025, that debate exploded again, and it's worth understanding why. Part 14, June 2025. The extraterrestrial technosignature debate explodes again. For decades, the search for extraterrestrial intelligence has been synonymous with radio telescopes scanning the sky for narrowband signals. The idea is simple. If an alien civilization wants to announce its presence, it might broadcast a beacon. If they're just doing their own thing, we might pick up leakage radiation from their communications or radar systems. Either way, radio is the obvious wavelength because it propagates well through space and through atmospheres. But in 2025, the conversation broadened significantly. A series of papers and conference presentations argued that technosignatures could appear in multiple forms across the electromagnetic spectrum, and potentially in dynamical or chemical signatures as well. Some fast radio bursts, those brief, intense pulses of radio emission from distant galaxies, were re-examined for features that might indicate artificial origin. While the consensus remains that FRBs are natural, probably related to neutron stars or magnetars, a minority of researchers pointed out that some of the timing and spectral patterns are difficult to explain with simple astrophysical models. Could they be beacons? Could they be byproducts of exotic propulsion systems? Probably not, but the questions are being asked seriously now. Meanwhile, optical CT programs looking for laser pulses have found a few candidates that remain unexplained. Most turn out to be instrumental noise or transient astronomical phenomena, but a few are persistent enough to warrant follow-up. And there's renewed interest in looking for megastructures, large-scale engineering projects like Dyson spheres, or stellar engines that would produce detectable infrared or optical anomalies around stars. Some exoplanet surveys are now including technosignature filters, checking for signs of industrial pollutants in exoplanet atmospheres or unusual reflectivity that could indicate artificial surfaces. The point is that the idea of finding technosignatures is no longer fringe. It's becoming mainstream, at least in the sense that reputable scientists are publishing papers, organizing workshops, and securing funding to look for them. NASA and other space agencies have started including technosignature searches in astrobiology missions. The James Webb Space Telescope, while not designed specifically for SETI, is capable of detecting atmospheric compositions that might indicate industrial activity. The shift is subtle, but real. We're moving from maybe someday we'll find aliens to let's actively look for them in multiple ways. This shift matters for how we think about 3i Atlas. If the broader scientific community is now willing to entertain the possibility that some astronomical objects or signals could be artificial, then an object like 3i Atlas can't be dismissed out of hand just for being weird. The burden of proof is still high. You need compelling evidence, not just anomalies. But the conversation has changed. It's no longer career suicide to suggest that an object might be a probe. It's a hypothesis that can be tested, debated, and refined like any other. Of course, there's pushback. Many scientists argue that we need to be careful not to see intelligence everywhere just because we're looking for it. The history of science is full of cases where natural phenomena were initially attributed to intelligence because we didn't understand them. Pulsars, when first discovered, were jokingly called LGMs, little green men, because their regular timing seemed artificial. They turned out to be neutron stars, entirely natural. Fast radio bursts were mysterious enough that some speculated they were alien signals. Now we know they're likely astrophysical, though still not fully understood. The lesson is that extraordinary claims require extraordinary evidence, and we should exhaust natural explanations before invoking intelligence. That's a fair caution. But it cuts both ways. If we reflexively dismiss any anomaly as natural without thorough investigation, we risk missing genuine signals. The balance is to take anomalies seriously, investigate them rigorously, and be honest about what we find. If the evidence points to a natural explanation, great. If it doesn't, that's when things get interesting. The cultural impact of this shift is already being felt. Public perception of SETI and technosignatures has changed. People are more aware, more curious, and more willing to consider that we might not be alone. The UAP, Unidentified Aerial Phenomena, discussions in the US Congress and elsewhere have normalized talking about unexplained objects and potential non-human intelligence. Whether those discussions are based on solid evidence or not is debatable, but they've opened a space in public discourse where these topics can be discussed without automatic ridicule. So when 3i Atlas comes up in conversation, it's not automatically laughed off as conspiracy theory. People ask questions. Is it possible? What would we need to see to confirm it? How would we respond? These are good questions. They reflect a society that's starting to grapple with the implications of contact, even if that contact is indirect through an artifact rather than a message or a visit. And as we're asking these questions about aliens and techno-signatures and what's out there, we're also rapidly advancing our own technology. We're building the tools that might someday let us reach objects like 3i Atlas, study them up close, maybe even reverse engineer them. In fact, in October of 2025, there was a breakthrough in autonomous space probes that might change how we think about interstellar exploration. Let's talk about that. Part 15, October 2025, the AI Self-Directed Probe, Breakthrough and What It Means for the Future. In October 2025, a research consortium announced the successful test of a self-directed space probe prototype. This wasn't just a spacecraft with autopilot. It was a system capable of autonomous decision-making, self-repair, adaptive mission planning, and even rudimentary learning. The prototype demonstrated the ability to navigate a simulated asteroid field, identify targets of interest based on scientific criteria, adjust its trajectory without ground control input, and diagnose and repair a simulated hardware failure using onboard resources. It was a proof of concept, not a flight-ready mission, but it represented a significant step forward in spacecraft autonomy. Why does this matter? Because deep space missions face a fundamental problem: communication delays. When you're sending a probe to Jupiter, the light travel time is between 30 and 50 minutes each way, depending on the planet's positions. That means a round-trip signal takes an hour to an hour and a half. If something unexpected happens, if the spacecraft encounters a hazard or an opportunity, waiting for instructions from Earth is impractical. The spacecraft needs to make decisions on its own. Traditional spacecraft have limited autonomy. They can execute pre-programmed sequences, stabilize themselves if they start tumbling, maybe avoid obvious collisions, but they can't improvise. They can't say, "This target looks more interesting than the one I was planning to observe, so I'll adjust." They can't diagnose complex failures and reroute systems creatively. Humans are still in the loop for most decisions. The new generation of self-directed probes changes that. They can operate independently for extended periods, making choices that maximize scientific return without constant oversight. The implications for exploring 3i Atlas are obvious. If and when a mission is sent to intercept the object, it will need autonomy. The mission might involve complex maneuvers, close approaches to assess the object's structure, attempts to sample material or dock with it if it turns out to have surfaces conducive to landing. All of this would happen faster and more dynamically than ground control could manage. A self-directed probe could adapt in real time, respond to surprises, optimize its approach based on what it discovers. But there's a deeper implication. If we can build self-directed probes now, in 2025, an advanced civilization could have built them thousands or millions of years ago. A probe that travels between stars would almost certainly need to be autonomous. The timescales are too long. The distance is too vast for remote control. It would need to navigate, repair itself, adapt its mission as conditions change, possibly even replicate or evolve over time. In other words, a von Neumann probe, a self-replicating machine that explores the galaxy systematically. This brings us to an uncomfortable parallel. If 3i Atlas is an alien probe, it's the equivalent of what we're now starting to build. It's a self-directed, long-duration, deep space explorer. Comparing it to our own technology makes it feel less fantastical. We're on the verge of creating machines that could, in principle, do what 3i Atlas might be doing. The technology isn't magic, it's engineering, advanced but comprehensible, and that raises existential questions. If self-directed probes become common, space becomes a domain of perpetual watchers. Not just human watchers, but autonomous systems from multiple civilizations, potentially overlapping, potentially interacting. Some might be purely scientific, others might have strategic or defensive functions. The possibility of non-biological intelligence operating in space changes how we think about identity, sovereignty, and security. There are also ethical and governance challenges. Who decides what instructions to give a self-directed probe? If it's autonomous, how do we ensure it behaves ethically? What if it encounters life or intelligence? Does it have protocols for first contact? Can it make decisions that affect entire worlds, like choosing whether to intervene in a planetary crisis or to remain a passive observer? These are not hypothetical questions. If we're building these systems, we need to think about their design and the values we embed in them. The race to build more capable autonomous spacecraft will accelerate, especially if 3i Atlas turns out to be something worth investigating up close. Nations and private entities will compete to deploy probes with the best AI, the most versatility, the longest operational life. The spacecraft themselves become assets, strategic tools, potentially even weapons if repurposed. The line between exploration and militarization blurs when the same technology that can navigate to Jupiter can also intercept and disable another nation's satellite. And then there's the speculative but fascinating idea of spacecraft evolution. If a self-directed probe can repair itself and has enough raw materials, can it build copies of itself? Can it improve its design over generations? In theory, yes. In practice, the engineering challenges are enormous. But if you give a sufficiently advanced AI control over manufacturing and resource extraction, and you send it into a resource-rich environment like an asteroid belt or a planetary ring system, it could bootstrap itself into something much larger and more capable than the original design. That's how you go from a single probe to a fleet, from exploration to colonization. We're not there yet. But the October 2025 breakthrough shows we're thinking about it. We're laying the groundwork for a future where autonomous machines operate far from Earth, making decisions that shape the trajectory of human presence in space. If 3i Atlas is a glimpse of what that future looks like from an alien perspective, it's both inspiring and sobering. Inspiring because it suggests that interstellar exploration is possible, that intelligence can reach across the void. Sobering because it reminds us that we might not be the first, and whatever comes next might not be under our control. So here we are, late 2025, approaching March 2026, watching an interstellar object fall toward Jupiter. We don't know for certain what it is. We don't know if it will capture or fly past. We don't know if it's natural, artificial, or something in between. But we know this. The questions it raises are fundamental. What is out there? Are we alone? Can we trust what we see? How should we respond if the answer to "are we alone" is no? Whether 3i Atlas turns out to be a comet or a probe, a random visitor or a deliberate explorer, it forces us to confront these questions. And maybe that's the real significance. Not the object itself, but what it reveals about us. Our curiosity, our fear, our ambition, our willingness to look up at the sky and wonder. In 2026, we'll have answers. Or at least we'll have new questions. And for a species that's always been defined by our drive to explore and understand, maybe that's enough.